Welcome students. Let us start our second lecture on number systems. Class 9th. In this lecture, we learn about decimal expansion of real numbers and conversion of decimal number into rational numbers. First, we discuss decimal expansion of real numbers. You already know that real numbers contain rational as well as irrational numbers. So firstly, we discuss about rational numbers. By actual division, we can easily evaluate 14 by 50. As you have done in your earlier classes, 14 by 50 is equal to 0.28. Next, our example is 11 by 3. In case of 11 by 3, the remainder does not become 0. Its quotient is 3.666 goes up to so on. So we put bar on 6, or we can say it is equal to 3.6 bar. Next example is 23 by 16. Its decimal expansion is terminating. Terminating means its remainder becomes equal to 0. 1.4375. Next is 11 by 15. It's again non-terminating and repeating. Here 3 is repeating again and again. So we put bar only on 3, not on 7. Next is 7 by 40. It's again terminating. And sixth is 8 by 9. Its decimal expansion is again non-terminating and repeating. Here 8 is repeating. So we put bar on 8. From here we conclude that there are two cases. First is case 1. Remainder becomes 0. Such decimal expansions are terminating, in which remainder becomes 0. Those decimal expansions are terminating, as in case of 7 by 40. 7 by 40, your fifth example, it turns out to be 0.175. 14 by 50 is also an example of case 1. In this case, the decimal expansions are terminating. 23 by 16 is also an example. Okay, second case is remainder never becomes 0. First is remainder becomes 0. Second, remainder never becomes 0. Such decimal expansions are non-terminating, recurring. Recurring means repeating. Non-terminating, repeating, or non-terminating, recurring. As we discussed, these examples, 11 by 15 is your 0.7333 up to so on. 3 is repeating, and decimal expansion is non-terminating, recurring or repeating. 8 by 9 is another example. Here 8 is repeating. 11 by 3 is also an example of case 2. So we discuss here two cases. First is decimal expansions are terminating. Second is decimal expansions are non-terminating, repeating. We summarize these results as the decimal expansion of every rational number is either terminating or non-terminating, repeating. Decimal expansion of every rational number is either terminating or non-terminating, repeating. Repeating and recurring, one and the same thing. Conversely, any number with terminating or non-terminating repeating decimal expansion is a rational number. If we have any number which is either terminating or non-terminating repeating, then we can say that it is a rational number. Without actual division, we can also check whether the rationals are terminating or non-terminating repeating. Without actual division, we can also check. Now rationals are terminating if denominator of a rational number is of the form 2 raised to power m into 5 raised to power n, where m and n are whole numbers. Where m and n are whole numbers means m and n can have any value starting from 0, 0, 1, 2, 3 up to so on. M and n should not be in fraction because fraction is not a whole number. For example, 14 by 50. This is equal to 0.28. This is terminating because here q is equal to 50. Denominator is equal to 50, which can be written as 2 raised to power 1 into 5 raised to power 2. 2 into 5 into 5. Is it clear? Next, non-terminating repeating. If q has prime factors other than 2 or 5. Terminating if q has prime factors only 2 and 5. Non-terminating if q has prime factors other than 2 or 5. For example, 11 by 12. This is equal to 0.916666. 6 goes on repeating. Here q equal to 12. Denominator is equal to 12. 12 can be written as 2 into 2 into 3. Here 3 comes. So it's non-terminating repeating. I think it is clear to you. Okay, next is our decimal expansion of irrational numbers. The decimal expansion of every irrational number is non-terminating, non-repeating. Non-terminating, non-repeating. For example, 0.02002, 0002, 00002 up to so on. This is non-terminating and non-repeating also. Another example. Third example, under root 2 is our irrational number. Under root 5 is also an example of irrational number. Cube root of 7. These all are irrational numbers. Pi is also an irrational number. The exact value of pi is not 22 by 7. 22 by 7 is an approximate value. Pi is an irrational number. Conversely, any number with non-terminating, non-repeating decimal expansion is an irrational number. Any number which is non-terminating as well as non-repeating is our irrational. Now we convert decimal numbers into rational numbers. Conversion of decimal numbers into rational numbers. Firstly, we convert terminating decimal numbers. We have already learned about two cases. First is terminating, next is non-terminating. First is conversion of terminating decimal numbers. Our example is express. First part is 0.35. Second part is 5.735 in the form P by Q. This is very simple type. You can easily solve. 0.35 can be written as 35 by 100 and you can cancel it and answer is 7 by 20. Next is 5.735. By removing decimal, you put 1000 over 5735 and answer is 1147 by 200. This is very simple case. Conversion of non-terminating repeating decimal number. This is important for examination point of view. Now we have to convert non-terminating repeating. First we convert 0.88888. Next we convert 0.631, 631, 631. Let us start our first. Let x equal to 0.8 bar. Mark it as first equation. Multiplying both sides by 10. We multiply both sides by 10 because here single digit is repeating again and again. Only 8 is repeating again and again. So we multiply it by 10. We get 10x equal to 8.8 bar. From 8.8 bar we mean 8.8888 up to so on. Now subtract 1 from 2. When you subtract left hand side from left hand side and right hand side from right hand side. 10x minus x is equal to 8.8 bar minus 0.8 bar. Left hand side is 9x and right hand side will be 8. Now you can find the value of x. which is 8 by 9. 8 by 9 is our rational number. So 8 by 9 is our answer. Now let us start our second part, 0.631 bar. Again, we take it equal to x. Let x equal to 0.631 bar. Mark it as equation 1. Now we multiply both sides by 1000 because 631, 3 digits. 3 digits are repeating again and again. If we have 0.79 bar, then we multiply that by 100. We have to count that how many digits are repeating again and again. How many digits? Here 3 digits, 631. So we multiply both sides by 1000. We get 1000x is equal to 631.631 bar. Mark it as 2. Now procedure is same. Subtracting 1 from 2, we get 1000x minus x is equal to right hand side, and after solving we get left hand side as 999x is equal to 631. From here you can easily find out x, which is your 631 by 999. I think up to this it is clear to all of you. Next question is express 0.134 bar in the form PYQ. Here is a little difference from previous question. In this only 3 4 is repeating again and again. 1 is single time. That is 1 is not repeating, but 3 4 is repeating again and again. Or we can say that this is 0.13434343434 up to so on. 3 4 is repeating again and again. So there is little difference. Let it be x. Now we have to shift 1 on left of decimal. For that we multiply both sides by 10 and we get 10x equal to 1.34 bar. Now question becomes same as that of previous questions. Now 3 4 bar, 2 digits are repeating again and again. So we multiply both sides by 100 and we get 1000x equal to 134.34 bar. Mark it as equation 3. Subtracting 2 from 3, we get left hand side 1000x minus 10x equal to 134.34 bar minus 1.34 bar, and it turns out to be 990 equal to 990x equal to 133, and your answer is 133 by 990. Is it clear? Okay. So Up to this our lecture. You can do practice about this, and you can contact me for any further queries.